Hello everybody, welcome into another lesson. So today we begin the trigonometry unit, which is going to take up about a quarter of this course. Now, I'm going into this with the approach that you've never had trigonometry before this. Now, those of you who took the Algebra 2 trig course with me have. Or if maybe you've had previous exposure in high school where a lot of Algebra 2 courses in a high school teach trigonometry. But if you were in college, you probably took a course called College Algebra, which is basically just Algebra 2 without the trigonometry. In my experience, in a Precalculus course, the split is about 50-50. So if you've had trigonometry previously, I do apologize for the next few sections that we're going to get into here. But I have to assume that it's entirely possible you've never had previous exposure to trigonometry yet. So I am going to take my time with these next three sections of trigonometry and really thoroughly break this down. Because after this course comes Calculus 1, which is assumed you understand trigonometry really well by then and you're able to do it. So let's get into this here. Today we're just going to talk about general angles and radian measure and arc lengths of circles. So when we talk about measuring angles, the one you're all probably most familiar with is degrees. You've probably been doing it since basic math and in geometry. But there's also radians. And largely when you get into calculus and other levels, and even a lot in this course, we're actually going to work primarily in radians. So there is a way to convert between degrees and radians, which we will get into before terribly long. And I have the graphing grid up because we're going to show you what these angles look like here at some point today. But what I would like to touch base with is degrees, minutes, and seconds. So you may or may not have seen DMS notation, which stands for degrees, minutes, and seconds. So let's say you have something like 64 degrees, 45 minutes. Well, we can convert this to a decimal. Why would you use degrees, minutes, and seconds? Is used all the time, definitely in nautical applications, so sailors use it all the time. It's more precise than trying to just use degrees with decimals. Also for pilots, they use it, or aerospace, those type of things. So you have your degrees, and it works largely the same like hours, minutes, and seconds when you're dealing with time. So your degrees are kind of like your hours. Your minutes are 1/60th of an hour, and then your seconds are 1/60th of a minute. So you have this in degrees and minutes and seconds notation. We need to convert this into a degree with a decimal. Well, this is going to be the same thing as 64 degrees plus 45 out of 60 degrees. Okay, so that 45 minutes is 45 out of 60 degrees. So what is 45 out of 60? Well, they both divide by 15, so that would end up being 3/4 of a degree. So this is going to give you 64.75 degrees. So that ends up being 64.75 degrees for 64 degrees and 45 minutes. what if you have negative 124 degrees in 30 minutes? Negative 124 degrees and 30 minutes. Okay, so you're going to find out today that we can have negative angles. And it's not that an angle is truly negative, it just indicates which direction it's going. So most angles go counterclockwise. That's where you have a positive angle, when it goes counterclockwise. If it goes clockwise, it's a negative angle. So that means it's not truly a negative angle, it just indicates which direction it's going. But negative 124 degrees and 30 minutes. So when you have a negative angle, you keep the negative sign outside of the parentheses you're about to create. You have then 124 degrees plus, that's 30 minutes, so that's going to be 30 out of 60 degrees, which would become negative of 124 degrees plus 1/2 of a degree. So this would turn into negative 124.5 degrees. So in decimal notation, this would be negative 124.5 degrees. All right, let's throw some seconds up there too. Let's say we have 85 degrees, 18 minutes, and then you're going to have 30 seconds. So yeah, your minutes have the single tick mark notation, your seconds have the double tick mark notation, okay? So how do we handle that to convert this into a single decimal, an 85 point something degree measure, okay? So what is a second? All right, so we know that 1 minute, or we know that there are 60 minutes in 1 hour, or I should say 60 minutes in 1 degree in this case, which would actually have to mean then that there are 60 seconds in 1 minute. So your minutes will cancel out. You'll end up getting 3,600 seconds in 1 degree. So here's how you're going to do this. You're going to take that 85 degrees plus, we know that 18 minutes is 18 out of 60 degrees, plus then you have that 30 seconds, so that's going to be 30 out of 3,600 degrees. Now that you've got everything in degrees, all you have to do is convert and bring everything together. So let's bring this into simplest form. You'll have 85 degrees plus, now 18 over 60 would actually reduce, you can divide both by 6, so you would end up getting plus 3/10 of a degree. Plus, all right, so 30 over 3,600 would break down into 3 over 360, which would be 1 over 120 degrees. So now you can simply add all these together and get a decimal approximation. And we're going to round the result to 3 decimal places. So this is why, you're going to see why we often prefer to use degrees, minutes, and seconds for nautical applications and things like that. Because if you just use an approximation, it can put you off a little bit. So 1 divided by 120 gives you an awful decimal plus 0.3. So you would get about 85.308 degrees. So when you add all these together, 85 degrees, 18 minutes, and 30 seconds is about 85.308 degrees. And it's about that. Just that little bit of difference, as you know, if you've done any type of navigating, can throw you way off from reaching your destination. Because it's subtle at first, but over time, it does make a difference as far as steering to where you're headed. That's why sailors and pilots and astronauts often use degrees, minutes, and seconds. All right, let's do one more. So we have 330 degrees in 25 seconds. So notice we have no minutes. And also you're going to find out today that we can have degrees greater than 180 because a full circle actually goes to 360 degrees. We're going to talk about angles that are greater than 180. So let's figure this out here. So we have no minutes, but that 330 degrees, 25 seconds is the same as 330 degrees plus 25 out of 3,600 degrees. Which we know 25 and 3,600 are absolutely going to reduce. That would turn into 1 over 144. So this would become 330 degrees plus 1 over 144 degrees, which now we can get a decimal approximation. This would be approximately 330 point, let's see what 1 divided by 144 is. 0.007. So 330 degrees 25 minutes, I'm sorry, 330 degrees 25 seconds is approximately 330.007 degrees. So that's how you would convert. Now let's work backwards a little bit. Let's say you're given 280.6 degrees. We need to convert this into degrees, minutes, and seconds. That's exactly what we need to do. Degrees, minutes, and seconds. So we know we have 280 degrees, right? This is the same as 280 degrees plus 6/10 of a degree. Well, in order to get this, to have any prayer of getting this in degrees, minutes, and seconds, we need to take that degrees here and make this a denominator of 60. So this would be the same as 280 degrees plus 36 out of 60 degrees, which once you have that denominator of 60, you would end up with 280 degrees and 36 minutes. That's exactly what this would convert into. This 280.6 degrees would convert into 280 degrees 36 minutes. Alright, now you have negative 115.8 degrees. How are we going to convert that into degrees, minutes, and seconds? Well, put a negative sign outside of the parentheses you're about to create. That 115.8 degrees, that's the same as 115 degrees plus 8/10 of a degree. which that 8/10, we need to convert that into a denominator of 60. So this would be negative of 115 degrees plus 48 out of 60 degrees, which that 48 out of 60 tells you it's 48 minutes. So this would be the same thing as negative 115 degrees and 48 minutes. That's exactly what you would have. Negative 115 degrees and 48 minutes. Let's see. We have negative 345.12 degrees. So we got negative 345.12 degrees. So again, put a negative sign, then do some parentheses. This would be 345 degrees plus 12 out of 100 degrees. Which is going to be the same. Now, this is where it gets kind of hairy, because you want to make this, first start with making this a denominator of 10. This is going to turn into negative of 345 degrees plus 1.2 out of 10 degrees. Well, we need to, in order to get the minutes, we have to make this a denominator of 60. So far we're going to be at a negative of 345 degrees plus 7.2 out of 60 degrees. So far, what we have is negative 345 degrees and 7.2 minutes. Well, here's the thing. That minutes we also want to get to be a whole number. We have a 0.2 minutes, which means if we have a decimal for the minutes, we can actually go all the way into seconds. So what we have now is negative of 345 degrees, 7 minutes, plus that 0.2 of a minute. That's the same as 2/10 of a minute. Which we also need to convert that denominator of 10 into a denominator of 60. So this would be negative of 345 degrees, 7 minutes, plus 12 out of 60 minutes. Well, a second is a 60th of a minute. So this tells you your final answer is going to be negative 345 degrees, 7 minutes, and 12 seconds. That's exactly what you would get. You'd end up getting negative 345 degrees, 7 minutes, and 12 seconds for your full-on measure. Let's do one more of these and then we'll move on. So let's say we have 310.75 degrees. So we have 310.75 degrees. Now actually, let's change that because I want to get some seconds in this. 310.35 degrees. So this is going to be the exact same as 310 degrees plus 35 out of 100 degrees. Well, it's going to be best, once again, if we go ahead and make this a denominator of 10 to start with. So this would be the same as 310 degrees plus 3.5 out of 10 degrees, which now what we have to do is get a denominator of 60 in order to be able to convert that to a minute. So this would end up being 310 degrees plus, now what is 3.5 times 6? That would be 21. So you'd end up having 21 out of 60 degrees. So that numerator of 21 tells you you have 21 minutes. Well, I guess it worked out where we still didn't have seconds. So 310 degrees and 21 minutes is what you'd end up getting. So 310.35 degrees is 310 degrees and 21 minutes. All right. So that's it for degrees, minutes, and seconds. Now, I think everybody has a good grasp on degrees. We've been dealing with those forever. But what you may not understand as much is the radians. And the radian measure is actually where we get, is actually what we base the circumference of a circle and the area of a circle on. So a full circle, we know a full circle is 360 degrees, right? Well, 360 degrees is the same as 2 pi. Because when you find the circumference of a circle, which is your perimeter, you're taking 2 pi. So a full circle is 360 degrees, which is 2 pi. Well, that means that half a circle, pi equals 180 degrees. So pi equals 180, right? You divide both by 2. So where am I going with this? If you want to convert degrees to radians, we're going to convert degrees to radians because you need to be familiar with both. You take your number of degrees times the pi divided by 180 degrees, because 1 pi is to 180 degrees. So then your degrees would cancel out. You would get your answer in terms of pi, which would give you radians. So let's go ahead and do that with some common angles here first. So let's say you have a 30-degree angle. 30 degrees, well, you're just going to take pi times 180, pi over 180 degrees, which would just end up giving you pi over 6. So pi over 6 radians is 36 degrees. So your answer in radians is going to be pi over 6. Let's say you have 150 degrees. So that 150 degrees, if you want to convert this to radians, you're going to take pi divided by 180 degrees. Well, this would be the same as, your degrees would cancel out. You would get 15 pi over 18. Well, 15 and 18 definitely reduce, right? They both divide by 3. You would end up getting 5 pi over 6. So 150 degrees equals 5 pi over 6 radians. What about 315 degrees? So you would take 315 degrees, still take that times pi over 180 degrees. Well, all right, 315 over 180, they both divide by 45. I can tell you right now, they both have common factors of 45. So 315 divided by 45 is 7. You would actually end up getting 7 pi over 4. So 315 degrees is the same as 7 pi over 4 radians. Let's do a 45 degree. So 45 degrees, that's going to be the same as 45 degrees times pi over 180 degrees, which would convert into pi over 4. So 45 degrees is the same as pi over 4 radians. Let's do a 60 degree. So notice we're trying to stick with the common angles, your 30s, 60s, and 45s. So we'll do the 90s and 180s in a second. So 60 degrees, that's the same as 60 times pi over 180 degrees, which would just give you pi over 3. So 60 degrees is equal to pi over 3 radians. All right, let's do 90. So 90 degrees, if you want to find that in radians, take that times pi over 180 degrees. Well, that would just give you pi over 2. So 90 degrees is going to be the exact same thing as pi over 2 radians. Okay, so what if we had 0 degrees? That should be fairly obvious. So 0 degrees times pi over 180 degrees, well, that would just equal 0. So in this case, 0 degrees equals 0 radians. That should make sense. Now 180 degrees, which would be a straight angle or half a circle, that's going to be 180 times pi over 180 degrees, which just gives you pi. So yes, 180 degrees equals 1 pi radian. That's exactly what you would get for 180. Another important one is going to be 270 degrees. So 270 times pi over 180 degrees, well, that's going to be 3 pi over 2 radians. So 270 degrees, which is 3/4 of a circle, equals 3 pi over 2 radians. And then we have, of course, let's do 360 degrees. So that would be times pi over 180 degrees, which would give you 2 pi, which is a full circle. So a full circle of 360 degrees equals 2 pi radians. All right, and then of course we can convert backwards. Let's go backwards from this. So if you want to convert from radians to degrees, we can definitely do that. So let's convert from radians to degrees. So if you want to, in general, convert from radians to degrees, you take your pi over n radians times 180 degrees over pi, and then you'll have your degrees. So let's do pi over 6 radians. If you want to convert pi over 6 radians to degrees, we know that there are 180 degrees to 1 pi radian. So your pi's would cancel out. You would be left with 30 degrees. So pi over 6 radians is the same thing as 30 degrees. That's exactly what you would get, 30 degrees. All right, so let's say you want to do pi over 4 radians. So you want to convert that to degrees. That's going to be the same thing as 180 degrees over pi, because there's 180 degrees to pi radians. Pi cancels out, you get 45 degrees. So that means that pi over 4 is going to equal 45 degrees. All right, let's do pi over 3. Let's convert pi over 3 radians into degrees. So this would be the same as pi over 3 times 180 degrees over pi. Once again, your pi's cancel out. You'd be left with 60 degrees. So pi over 3 radians would equal 60 degrees. And all these radians to degrees are very important. Notice I'm sticking a lot to the special triangles, like your 45, 45, 90, and 30, 60, 90 right triangles. Those come up all the time. All right, pi over 2 radians. So this would be pi over 2 times 180 degrees over pi. Well, pi would cancel out. You'd just be left with 90 degrees. So pi over 2 radians equals 90 degrees. What about, let's take 3 pi over 4. 3 pi over 4, so you would take then 180 times 180 degrees over pi. Well, your pi's for sure cancel out. 4 goes into 180 45 times, so you'd end up with 3 times 45, which would give you 135 degrees. So 3 pi over 4 radians equals 135 degrees. That's exactly what you would end up getting. All right, so I think we have a good grasp on finding radians and degrees to radians. Now, let's sketch some of these angles. So, let's say you're being asked to sketch a 30-degree angle. And these are going to be rough drawings. 30 degrees, which we know is the same as, if you want to do the conversion, you can. This is the exact same thing as pi over 6 radians. So, in standard position, the x-axis, if it's a positive angle, you're going counterclockwise. So a 30-degree angle looks roughly like so. That's about a 30-degree angle. So you start from the x-axis and you're going counterclockwise. That's about a 30-degree angle, or pi over 6 radians. And notice you're in the first quadrant. And of course your x-axis here is 0 degrees. let's increase this a little bit. Why don't we go to 45? So let's sketch a 45-degree angle, which is the same as pi over 4 radians. So that's going to come up a little bit more. That's going to take up half of the first quadrant. So there's a 45-degree angle. Right there, notice I have the notation of it going counterclockwise because it's a positive angle. That's 45 degrees roughly equals pi over 4. And of course, let's do 60. That's going to come right about here, roughly. So what we're sketching, of course, this time is a 60-degree angle, which is the same as pi over 3 radians. It's good to be able to interchange degrees and radians. It's very important that you can. So there is a 60-degree angle, which is pi over 3 radians, which would leave 90 degrees next. So we're going to sketch 90 degrees, which is the same as pi over 2 radians. All right. So what's a 90-degree angle in general? It's a right angle, isn't it? Well, we notice right here at the origin, the y-axis forms a perfect 90-degree angle or right angle with the x-axis. So starting from here all the way to this area, that's a 90-degree angle. That is your positive y-axis, is a 90-degree or pi over 2 radian angle. So here's everything in quadrant 1. This is quadrant 1. Everything's easy there. Now where it gets a little bit hairy is going to be quadrants 2 through 4. So let's get into quadrant 2. Let's sketch a 120-degree angle, which, why don't we convert that to radians? So 120 degrees times pi over 180, that's going to equal 2 pi over 3 in terms of radians. So 120 degrees is 2 pi over 3 radians. Well, how do we also address its measure? If you have any other quadrant but quadrant 1, you have to deal with what's called a reference angle. Reference angle. So if you're in the second quadrant, I think it's plain to see that if you go all the way to the negative x-axis straight back, that would be 180 degrees. Because you would have a straight angle. That would give you 180 degrees. So if you're in the second quadrant, to find your reference angle, you're going to take 180 degrees minus your degrees. So it's going to be based off of 180. So in this case, it's going to be 180 degrees minus 120 degrees. This would be treated like a 60-degree angle, only it's in the second quadrant. So your reference angle is actually a 60-degree angle. Or if you want to do this in radians, you would take pi minus your radians. In this case, you would have pi minus 2 pi over 3, which means your reference angle is going to be treated like pi over 3. So it would be like a pi over 3 angle, only located in the second quadrant. So let's sketch that real quick. So let's do 2 pi over 3, treating it like a 60-degree angle in the second quadrant. That's going to start still at 0 and go all the way over here. So there's roughly a 120-degree angle. Now, of course, we could end up doing, next would be 145, sorry, not 145, 135. So let's sketch a 135 degree angle. And why don't we find that in radians? So 135 degrees times pi over 180, that's the same as 3 pi over 4 radians. So 135 degrees is going to be the same as 3 pi over 4 radians. In this case, what's your reference angle? You're going to end up having 180 minus 135, which in actuality is going to end up giving you a reference angle of 45 degrees. So 135 degrees is exactly a 45 degree angle in the second quadrant. Or if you want to do this in radians, you would take pi minus pi over 4, which is going to end, minus 3 pi over 4, which would give you a reference angle of pi over 4. So you would treat this like a pi over 4 angle in the second quadrant. So here is going to be roughly your 145 degree angle. Again, we start and go counterclockwise, so there is roughly a 135 degree angle. All right, let's do 150 degrees. In this case. So we're going to sketch a 150 degree angle. Well, 150 degrees is going to end up being, let's convert this to radians, times pi over 180, which would end up becoming 5 pi over 6 radians. So 150 degrees equals 5 pi over 6 radians, which is going to look roughly like that. Let me sketch that angle real quick here, going counterclockwise since it's a positive angle. So there's your 150 degree angle roughly. Now we can find the reference angle. So it's going to be 180 minus 150 degrees, which tells you that your reference angle is actually 30 degrees, or pi minus 5 pi over 6 would give you a reference angle in radians of pi over 6. Now, why do we bother with reference angles? Well, okay. Some people make the big mistake. They think once you get past the first quadrant, you subtract 90 from your angle, which they would end up then treating something like 150 degrees like a 60 degree angle, which would actually give you false values. That would give you the complete opposite of what you're trying to do. So you really have to take the 180 degrees as your reference. And really anything along the x-axis is always your reference angle. Alright. And of course, why don't we sketch 180 degrees? I think it's pretty clear what your reference angles are going to be in this case. So let's do 180 degrees, which we know to be pi radians. Well, that's just going to be the whole x-axis, right? So you start at the positive x-axis, go counterclockwise to the negative x-axis. You have a straight angle. That's 180 degrees. That one's easy enough. And this ties up quadrant 2. So there's quadrant 2. Now we're going to get into quadrant 3, where everything changes. Yet again. So reference angles change a little bit in the third quadrant. So let's do a 210 degree angle. Well, why don't we convert that to radians? So 210 degrees times pi over 180 degrees is going to equal 7 pi over 6 radians. So 210 degrees equals 7 pi over 6 radians. So let's sketch that 210 degree angle. Which would look roughly like that. Still going counterclockwise because it's a positive angle, so there's about what you end up with. So yes, this is proof you can have greater than 180 degrees. Now, a reference angle in the third quadrant is going to be, you take your actual angle. So this time you take your actual angle minus 180. So we have 210 degrees minus 180, because 210 is greater than 180, you'll just have a reference angle of 30 degrees. So the 210 degrees behaves as a 30 degree angle in the third quadrant. Or if you want to do this in radians, you take the number of radians minus pi. In this case, that's going to be 7 pi over 6 minus pi, which would behave as a pi over 6 angle in the third quadrant. This is where you definitely wouldn't want to be adding to 90 or subtracting 90 from it, because that can throw you way off. That would give you a 120 degree reference angle, which itself is not a reference angle. That would give you another 60 degrees when really it should be a 30 degree reference angle. So that can really throw off your values. All right. Let's do a 225 degree angle. So let's do a 225 degree angle, which let's convert that to radians. So 225 times pi over 180 degrees, well, that's going to equal 5 pi over 4. So 225 degrees is the same as 5 pi over 4. So let's go ahead and sketch that. That's going to take up roughly half of the third quadrant. I did it in green on accident. Oh well. Well, here it's going counterclockwise because it's a positive angle. So there is your 225 degree angle. Now, what's your reference angle? So you're going to end up taking then that 225 degrees minus 180, which would treat this as a 45 degree reference angle. Or if you want to do it in radians, you take your 5 pi over 4 radians, subtract pi, you end up getting a pi over 4 radian reference angle. And then one more in the third quadrant. Well, technically you could argue 2 more, depending upon how you look at it. Let's do a 240 degree angle. So we are going to do a 240 degree angle. So let's convert that to radians. 240 degrees times pi over 180. Well, that's going to be the same as 4 pi over 3. So 240 degrees is the same as 4 pi over 3 radians. So that's going to look roughly like this. So there is your, we're going counterclockwise because it's positive. And there's your 240 degree angle. Now what's your reference angle? Well, you're going to take that 240 degrees minus 180 degrees. This actually acts as a 60 degree reference angle. Or if you want to do this in radians, take 4 pi over 3 minus pi, you would just get a pi over 3 reference angle. All right. And then, of course, let's do the 270. Let's do 270 degrees, which is 3/4 of a circle. That's the same as 3 pi over 2 radians. So start at your standard position here. Well, yeah, it's going to go down to the negative y-axis. So start at your standard position, go counterclockwise. There's your 270 degree angle, 3/4 of a circle. And it's just the negative y-axis. So here's quadrant 3. And of course, we got to cover quadrant 4. Reference angles change yet again in quadrant 4. You'll see how in just a minute. So let's do a 300 degree angle. Let's do 300 degrees. Let's convert that into radians. And again, a lot of you are going to make the mistake, or might make the mistake that, well, you just subtract 270 from 300, you would get a 30 degree reference angle. Actually, that's not how it works. You actually, in the fourth quadrant, you start with 360, since that's your x-axis. Subtract 300 from that, you would actually find that's a 60 degree reference angle in the fourth quadrant. So 300 degrees times pi over 180 to convert to radians is actually going to give you 5 pi over 3 radians. So 300 degrees equals 5 pi over 3 radians. So let's go ahead and sketch that real quick. That's going to put you about right there. Going counterclockwise from the starting position, there's your 300 degree angle. Now, what is a reference angle in the fourth quadrant? So in degrees, you would take 360 degrees minus your degrees, you get your reference angle. So in this case, it would be 360 degrees minus 300 degrees, which would mean your reference angle is a 60 degree angle in the fourth quadrant. And then, if you want to do this in radians, so 360 degrees, that'd be 2 pi minus your radians. So in this case, 2 pi minus 5 pi over 3 would just end up giving you a pi over 3 reference angle. All right, let's do a 315 degree angle. So 315 degrees is what we're going to do. Well, let's convert that to radians first. So 315 degrees times pi over 180 degrees would end up actually becoming 7 pi over 4. So 315 degrees is the same as 7 pi over 4 radians. So what would that be in terms of a reference angle? So you're in the fourth quadrant, take 360 minus 315 degrees, you would actually get that this is like a 45 degree angle in the fourth quadrant. So we have enough to sketch that. It'll take up half the fourth quadrant, so start at your starting position, and that's about what it's going to look like. Starting to look more like a Pac-Man mouth, isn't it? Okay. For a radian reference angle, so take 2 pi minus 7 pi over 4, you'll get a pi over 4 reference angle. All right. And then, of course, let's do a 330 degree angle. All these ones I'm doing today are based on special values of the 45, 45, 90, and 30, 60, 90 right triangle relationships, which really do come into play from geometry in this course and in future courses. So 330 degrees, let's convert that to radians. So 330 times pi over 360 degrees, that's going to be the same as 11 pi over 6. So you would end up getting 11 pi over 6. So your reference angle is going to be 360 minus 330 gives you a reference angle of 30 degrees. Or in radians, you would take 2 pi minus 11 pi over 6. That would give you a reference angle of pi over 6. So now we can sketch that. And there is going to be your 330 degree angle. Let's denote that it's going to be, of course, 11 pi over 6. All right. Now, whoops, that should have been pi over 180. Well, I ended up getting the radian measure right, but I set it up wrong. It's really pi over 180 here, but still 11 pi over 6 is correct. But anyway, let's go ahead and sketch a 360 degree angle. We'll have come full circle. How would you denote a 360 degree angle? So we know 360 degrees is 2 pi radians. Well, you're going to start in your starting position for 360, go all the way back to the positive x-axis, and see where that arrow touches the positive x-axis? That denotes a full revolution counterclockwise around the circle. That's a 360 degree angle. So now we have discussed all the special angles in the coordinate plane in quadrants 1 through 4. Okay. Well, why don't we also talk about when you have an angle greater than 360? What if you were asked to sketch a 420 degree angle? Angles can go on infinitely, but keep in mind, a full circle is only going to be 360 degrees. So that means if it's greater than 360, you're starting a whole nother revolution around the circle. If it's greater than 360 degrees, what you got to do is subtract 360 degrees, and you would get that this would be a 60 degree angle, or it would be in the first quadrant. So let's sketch a 420 degree angle. So we know that's going to be roughly what? A 60 degree angle there? Okay. So you're of course going to go counterclockwise. Since it's a positive angle, you go all the way around till you reach that 60 degree again. That is going to be your 420 degree angle. Those are what are called coterminal angles. Coterminal angles can be found by adding or subtracting 160. So, I think we know what the quadrants are by now. Okay, so let's say we wanted to sketch a 720 degree angle. If you subtract 360 from that, you'll get 360. That would actually be 2 full revolutions around the circle. Positive angle, we're going to go counterclockwise, so that'd be 1 revolution. Here's another full revolution. So there's 2 full revolutions around the circle. There's your 720 degree angle. You end up right back at the starting point. Now this is the business of angles can be negative. Let's do a negative angle. Let's go negative 45 degrees. So what the heck are we going to do with a negative angle? Well, a negative angle means you're going to start at the starting position, but since it's negative, you go clockwise instead of counterclockwise. So this would be a 45 degree angle in the 4th quadrant. So at the starting position, you actually end up going clockwise. That's a negative 45 degree angle. Again, it's not that the angle's negative itself, it's just that it is going clockwise as opposed to counterclockwise. Now the good news is, though, you can find coterminal angle measures for this. So if you want to find the coterminal angles, take that negative 45 degrees and then add 360 degrees to it, you'll end up getting an angle measure of 315 degrees. So that means this would be the exact same measure as if you were doing a positive 315 degree angle. Or if you want to find another negative angle for it, take that 45 degrees and subtract 360 degrees, you would end up getting negative 405 degrees. So that would actually mean you went clockwise around the circle once and then going all the way to 45. So I would be going all the way back around one time and then back to that 45 degree angle in the 4th quadrant, going clockwise. So there's my negative 405 degree angle. All right, why don't I sketch a negative 120 degree angle? So negative 120 means, again, I'm going clockwise this time. So if I'm going clockwise, that's going to put me actually in the 3rd quadrant, which would put me right here. So there's my negative 120 degree angle from the starting position, because I'm going clockwise, so it's negative. If I want to find coterminal angles, I would add 360 degrees to that. So negative 120 plus 360, that's going to be the same as a positive 240 degree angle. So that would be the same as if I went clockwise down to 240 degrees, it makes no difference there. Or if I want to find a coterminal angle that's negative, take negative 120 minus 360, you would end up getting negative 480 degrees. They would both be the exact same thing. All right, negative 90 degrees. That means I'm going to form a 90-degree angle going clockwise. So you start at your starting position. I'm actually going right here for my negative 90. So if I want to figure out some measurements for that, I can find a coterminal angle by adding that to 360. Negative 90 plus 360 would give me a 270 degree angle. So negative 90 is the exact same thing as a 270 degree angle going counterclockwise. Alright, now negative 180 degrees, that's going to be this time going clockwise from the starting position. That would put me all the way over here. There's my negative 180 degrees. If you add it to 180 degrees, if you add this to 360, you would get positive 180 degrees. That's the only time it's the same, whether positive or negative. Alright, how about a negative 270 degree angle? Negative 270 means I'm going clockwise 3/4 of a revolution, so that'll put me up here. And if I added this to 360, that'd be the same thing as a positive 90. That equals a positive 90 degree angle. And then I think it's self-explanatory. If you did negative 360 degrees, that's a full revolution clockwise. You would just be going all the way around clockwise. All right. So those are all your coterminal angles, reference angles, all the angles of the quadrants. Now, one last thing we got to talk about is called arc length. You can find the length of an arc of a circle. So arc length, your length is denoted as S. That equals your radius times your angle theta. That angle is going to be in radians. So this formula works only in radians. It doesn't work in degrees. So let's say in this case you have a radius equal to 14 inches. And your angle is 180 degrees. Well, you probably would want to convert that 180 degrees to radians, which we know is pi radians. So your arc length is going to equal 14 inches times pi, which will round the result to 2 decimal places. pi, that gives you about 43.98 inches. So the length of the arc with a 14-inch radius and the central angle being pi radians is going to be 43.98 inches. All right. Now this time you have a radius of 9 feet. The central angle that encloses this arc is a 60-degree angle. So we want to convert that into radians. That's going to give you pi over 3. So your arc length is going to end up being that 9 feet times pi over 3, which would just give you 3 pi feet, which now we can get a decimal approximation to 2 decimal places. Let's figure out what the heck 3 pi is. It's about 9.42 feet. So the length of the arc with a radius of 9 feet and a pi over 3 radian central angle is about 9.42 feet. All right. Let's do a radius of 12 centimeters. This time they give you the measure in radians. The radius of this section of the circle is 12 centimeters. The central angle is 3 pi over 4 radians. So your arc length is going to equal that 12 centimeters times that 3 pi over 4, which would actually end up then giving you 9 pi centimeters, which we'll find out about what that is for 9 pi. That's about 28.27 inches. Or centimeters, excuse me. So you would get an arc length of approximately 28.27 centimeters. Now, we can also work backwards a little bit with this formula. This time, they give you the arc length and the angle. They want you to find the radius. So that means you can find the radius by taking your arc length and dividing it by your central angle in radians. So in this case, they give you that your arc length is going to be 36 feet. Your angle is going to be pi over 2 radians. So your radius is going to equal that 36 feet divided by pi over 2, which would end up being the same as 36 feet over 1 times 2 over pi, which would end up giving you 72 feet divided by pi, which now we can actually do a radius. So 72 divided by pi gives you about 22.92 feet. So the radius is going to be approximately 22.92 feet for that section of the circle. Let's do one more of these, and then we'll be done with the lesson. I know this was a lot to cram in, but all very important. Wow, so they give you an arc length of 85 miles. 85 miles, giving you 135 degrees, which we know to be the same as 3 pi over 4 radians. We need to find the radius. So the radius would equal that 85 miles divided by that 3 pi over 4 radians, which is going to give you 85 miles all over 1 times 4 over 3 pi rather. So 85 times 4 is going to be 340 miles divided by 3 pi. And now we can get an approximation for our radius. we get about 36.08 miles. So the radius of that region is about 36.08 miles. So that's it for this lesson. Next lesson, we're going to talk about the unit circle and different things with trig functions. We'll actually bring in like sine and cosine and tangent and secant and cosecant and cotangent. So I hope everyone has a great day. Take care.